Apparently, I accidentally paused the recording as I was about to get to number 10. But, maybe it's a good place to take a break anyway. So, dig this. For number 10, we got the GIntercept. You should have seen, guys. I was here recording like a whole bunch of stuff, and then I got to the end of it, and it was, I messed it up. Oh well. So, GIntercept here, once again, GIntercept means you put a 0 in for R. That will be pretty much like you would figure from the last one. It's just a different looking function, so I wanted to take you through it. But that would be us just saying 0, 0, 0, plug in 0 for R, and we'll be all right. And so we have 4 times 0 to the, not to the R, to the fourth, plus 28 times 0 to the 3, plus 24 times 0 squared. It doesn't matter, because 0 times anything is 0 to the fourth is still 0. It doesn't really matter. 0 to the fourth is 0. It's just 0 plus 0 plus 0. And so we just have 0. I guess it'd be the output. You plug in a 0, you get out a 0 here, because every term has an R in it. And so they'll all be zeroed out. That's not why I brought this question up, though, but it's good insight, I guess, Here's the other part. Wanted to mention this, too. For the RIntercept, though, that means we're making the G part 0. And so we'll just zero that part out, but it's hard to figure out how to solve this. Like, what the heck? How do I solve for R when the G part is 0, and the function value is 0? Well, that's not easy to do unless you remember we can factor this thing, make it look like the other one, And so if that's the case, I'm looking at this, I notice that they all have some R's in them. R's there, R's there, R's there. R's, 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 And so maybe let's just take a couple of R's out or whatever, some kind of a common factor. And so let's see what we could do. It looks like 4 goes into everything, so I could take out a 4 and maybe a couple of R's out. And then we'd be left with like R squared plus 7R plus 6, I believe. And then that part, you'll notice, can factor even more. So I'll keep the 4R squared, and then we have R plus 6 and R plus 1. If we're equaling this out to 0, now we could probably solve that out. And so we'll say, well, I'll take it in pieces. Either 4R squared is 0, or R plus 6 is 0, or R plus 1 is 0, like we do. Now if R plus 6 is 0, negative 6 plus 6 is 0, so negative 6 is the R. And same thing here, R must be negative 1 because of the same idea. But 4R squared being 0 may not be as obvious to you. If you see it, just go with it. But if you don't see it, you can solve it out. You can be like, well, I'll divide the 4, I guess. And then I have R squared equals 0 still, because 0 divided by 4 is 0. But then something squared equals 0, the only thing squared equals 0 is 0. So I guess we'll just say R is 0 in the first place. So that's interesting. And so then we have, I guess, R is 0, or negative 6, or negative 1. And you just put those in there. Again, you can put them in ascending order from smallest to biggest, or whatever else, And so I think this is probably the safest order in which to put them. Let me know if that's not the case. Cool. Okay, what else? Oh, I was supposed to erase this. Don't look at anything. There we go. All right, pretend that wasn't there. But then we have, because remember I recorded it and then I messed up the recording. Okay. So same idea, just a weirder looking function. Wanted to give you my take on this. If I saw something like this, what I would do is XIntercept. Remember, that means the y value is 0, the function value is 0, and we just say 0 equals minus x3 plus 6, and then solve that out. Probably we'll get the x by itself at this point. And so if we have that, maybe we'll move this minus x to the 3 over to the other side, plus x to the 3 plus x to the 3 or something. And then we'll have x3 equals positive 6. And from there, we'll just, maybe we'll 3 root it to solve that out. And now we have just x equals the 3 root of 6, and that'll work out. And so you could say that if it's an x to the 3, I would expect there to be 3 solutions, and there are. But maybe sometimes you get 2 imaginary solutions, and they're funny that way. This one, I think, actually really what the issue is we just have 3 copies of the same solution. So they're all just a cube root of 6. We call that, it's the solution with multiplicity 3 because there's 3 of them. But whatever, anyway, the only x-intercept, it's just one of them because it only hits the x-axis once. Who cares, though, about all that? So, anyway, so that's how we solved that one. That's what I would do if I saw it. And then f of x-intercept, or the y-intercept, that's what happens when you put 0 for the x part. And that part will be easy enough. We could say, well, that's just like plugging in 0 for x. And so that'll be a minus of 0 to the third. Let me work on my 0 drawing. Not getting any better. 0 to the third plus 6, and then from there we just look at it, I guess. 0 to the third is 0, and it doesn't matter if it's negative, it's just, it's whatever. It's just 0 plus 6, and 0 plus 6 is 6, and so that's what we're looking for there. That's what I would do there. Okay, I wanted to, here, let's pretend like we were looking at this one. It's interesting, but not as interesting as the next one that's like it. And so, interesting on this one, guys, let's see. We have y-intercept and x-intercept. That's just like we've been doing, so we'll do those real quick. The y-intercept is when the x is 0, so we'll 0, 0, 0, and then that's going to be like it goes. So 0 minus 8, 0 plus 8, 8, whatever. And then 5 times 0 minus 2. And then we'll just see how that goes. This is negative 8. This is 8. This is, let's see here, 5 times 0 is 0. So 0 minus 2 is just negative 2. And then we'll times them. The negatives will cancel, That's 128, I think. And so we'll be good there. We'll times it, and it's good. Now, its x-intercepts are whatever. Let's figure that out as well. Stop it. Okay. There we go. I'm erasing. Oh, already picked out a pen. So it's x-intercept. That's when the y part is 0, or in this case, the p of x part is 0. So we'll 0 out the p of x part, and then we have x take away 8. X plus 8. And then, what's with the 8s? I don't know how to draw them. And then 5x minus 2 is 0. And we'll just solve them each for 0. If x minus 8 is 0, x plus 8 is 0. And 5x minus 2 is 0. And we'll do like we do. Some number take away 8 is 0. Some number minus 8 is 0. That would be just positive 8, I guess. And then some number plus 8 is 0. So that number would be negative 8, I guess. So x is negative 8. And then here it's not as obvious. If you see the answer on this one, if you can just see it, then go with it. But if you don't see it, it's okay just to do it algebra style until you get used to them. So we can say, well, if it's a minus 2, I'll plus the 2 to get rid of it. And then I have 5x left over equals 0 plus 2, which is 2. And then I'll divide the 5 times 5, so you divide the 5. And then we have x equals just 2 divided by 5, or just 2 over 5, I guess. Giddy up on that, And so now we got ourselves 3 x-intercepts. They are negative 8. Whoops. Let's work on the old penmanship there. Negative 8, positive 8, and positive 2/5. Oh, but now they're mentioning make sure that they're in order with one as they go greater. So let's see here. 2/5 is bigger than the negative, but 8 is bigger than 2/5. So I guess we'll put it in that order. And then the other reason I wanted to bring this up is because now we got ourselves, okay, full disclosure, I just paused it and then came back, and I can't remember what sentence I was in the middle of a second ago, whatever it was. Anyway, wanted to talk to you about whatever these are, the end behavior of the function, or the long run behavior. We've talked about these before, just not with this kind of a function. This one's not foiled out like the other ones were. This is still in factored form, which is nice. It's all linear factors. It's good. But it makes a different challenge for this. So let's look at this real quick. So the long-run behavior, or the end behavior of the function, if we say as x approaches infinity, what's happening with the y values, And so let's see. As x approaches infinity, that's like plugging in a positive, giant, huge number, like 1,000,000 or something, and seeing what happens to the output value or the y value. And so we'll just see. If I plug in, let's just go ahead and do that. We'll plug in giant numbers. And so if we plug in giant something, let's see here, 1,000,000-ish. That's only 100,000. There we go. It's a weird looking zero. It doesn't matter. It's some big old number. -8. We're just plugging it into the function. There's a -8, then I have 1,000,000. I'm just going to do cursive zeros. +8, cursive zeros, and then the last one is you plug in at 1,000,000 there, so it'd be 5 times 1,000,000 -2. And then we'll just see what happens to the function. And so remember, we're paying attention. Does this thing end up going way, way positive huge number, or does it go way, way negative huge number? Or does it do neither of those and kind of start tapering down into a small number somehow? I don't think this is going to get to a small number, but let's see what happens. If I have 1,000,000 take away 8, 1,000,000 take away 8 is still almost 1,000,000, so that's a giant, huge number, but it's still positive. Now 1,000,000 plus 8 is 1,000,008, so that's also positive because it's 1,000,008. And then even more than that, we have 5 times 1,000,000 is 5,000,000. Take away 2 is just almost 5,000,000. Still, it's 4,000,000 something, and so, but it's positive. There's no reason for that to be negative that I can see. It's just 5,000,000 take away a little bit. That being the case, these are all positives. So positive times positive times positive is still a positive number. So we'll say when I plug in a giant number like 1,000,000, a positive 1,000,000, what I get is a positive, humongous number, or a giant positive. And so that's what we'll say about this, is we'll say what we get is a giant positive number when we plug in a positive infinity, or as we approach infinity. And then we'll play the same game for negative infinity. I think I may have misspelled the word huge there. I might have just written the word hug. So giant positive hug number. But if we plug in a negative 1,000,000, as we approach negative infinity, that's like plugging in a -1,000,000. Who cares about the zeros? We'll just do cursive. That would be negative 1,000,000, take away 8, negative 1,000,000 plus 8, and then 5 times negative 1,000,000 -2. And then we'll just see what that behavior ends up looking like. Will it be a giant positive or a giant negative? And so this is negative 1,000,000, take away 8 is still a big negative. Negative 1,000,000 plus 8 is still negative 1,000,000, almost. It's a giant negative, almost 1,000,000. And then 5 times negative 1,000,000 is negative 5,000,000. Take away 2 is even more negative. This is negative 1,000,000 or 5,000,000 too, but it's negative, And so that's a negative times a negative times a negative. Giant negatives. These are giant negatives. No wonder I'm writing them so big. Anyway, so we have negative times a negative times a negative. It ends up being negative in the end. You could cancel the first 2 if you want, but it's negative in the end. Some giant negative number. Huge negative. And so we'll say if we plug in huge negatives as we approach negative infinity, the output of the function is also giant negative. Even gianter negative. More giant. Something like that. Anyway, that's all I got. That's all she wrote.